I'm hoping you're well. Welcome back to my YouTube channel. A chilly morning it is today in Nairobi. Uh, on this particular video, I'll be taking you through a topic on wide area network technologies, so WAN technologies. Now, an economic globalization and digital transformation accelerates. I'm hoping you're well. Welcome back to my YouTube channel. It's a chilly morning in Nairobi City. On this video, I'll be taking you through the topic on wide area network technologies. So I will read the forward. As economic globalization and digital transformation accelerate, enterprises keep expanding their scales. So more and more branches located in different regions, with each branch network being considered as a local area network. The headquarters and branches need to cross geographical locations in order to communicate with each other. To better carry out services, an enterprise needs to connect these geographically dispersed branches through a wide area network, also referred to as a WAN. The development of WAN technologies is accompanied by the continuously increased bandwidth. In early stages, we had the X.25, which provided only about 64 kilobits per second bandwidth. Later on, the digital data network and frame relay also were developed, and they increased. They were developed and they increased frame relay. They increased the bandwidth to 2 megabits per second. After that, we had SDH, which is called synchronous digital hierarchy, and also ATM. So SDH and ATM, which further increased the bandwidth to 10 gigabits per second. Now the current IP-based ones provide 10 gigabits per second or even higher bandwidth. So this course will describe the development history of WAN technologies, especially the implementation and configuration of point-to-point protocol and also point-to-point protocol over Ethernet, PPOE. By the end of this chapter, you should be able to understand the basic concepts in the development of the development history of WANs, also understand PPP and PPOE implementations, PPP and PPOE configuration, and also some basics about MPLS and SR segment routing. Okay, so let's begin by looking at an overview of early WAN technologies. So what is a WAN really? What is a WAN? Now, we know that by definition, a local area network is a network that covers a small geographical area, while on the other hand, a WAN is a network that covers a long distance. They cover large geographical areas. Sometimes they can even be international. They connect multiple regions like cities or countries. So that is what we call a WAN, a wide area network. Now, really, most of the time, whoever provides the WAN interconnection is actually the internet service provider. The internet service provider is the one that provides the WAN connection. Okay, so what is the main difference between a LAN and a WAN? So one of them we've just said, of course, is the coverage area. The LAN covers a smaller area, geographical area, while the WAN covers a huge geographical area. WAN interconnect LANs, and these particular LANs are interconnected via the internet service provider network. Uh, via the internet service provider network. Now, uh, the other thing is that for LANs, they normally use switches, for example, at the aggregation and the access layer. On the other hand, for WANs, they mostly use routers. They mostly use routers and do not really use switches at any point. Again, we know that LANs belong to organizations, while, as I've mentioned earlier, WANs belong to the internet service provider. Mm, mm. Now, WANs and LANs use different protocols at the data link layer. They use different protocols at the data link layer. Now, we've already learned about the Ethernet. The Ethernet. The Ethernet. Or 802, is it 802.3? 802.3 standard. We've also learnt about wireless, WLAN, the 802.11 standards. So at the data link layer, LANs use these technologies. On the other hand, with the WANs at the data link layer, they use PPP, the point-to-point protocol, which we are going to look at. Now, on the other upper layers, like the network layer, transport layer, and the other layers, upper layers, they operate with the same manner. So the only difference is indeed here on the data link layer, where they differ in terms of the protocols that they use. So that's why we're going to learn PPP. We're going to learn about PPOE, which are protocols that are used at the data link layer of the WAN technology. Okay. Now, let's have an overview of wide area network technology. Now, the early WANs and LANs differ in data link layer and physical layer, and are the same in other layers in the TCP/IP reference model. Now, as you can see here, here they are the same. LAN technologies and WAN technologies on the upper layers from layer 3 there, they are the same. They are the same. On the other hand, the difference comes in. The difference comes in here at the data link and physical layer. Now, for example, at the data link layer with LANs, we normally use the 802.3 standard and also .11 standard, which we've looked at. And when it comes to the physical media, we, for example, use the Ethernet cable or fiber, or we also use wireless radio. On the other hand, for WAN technologies, we can use protocols such as PPP, HDLC, frame relay, ATM, and normally with WAN technologies we use serial cables like RS-232 or V.24 or V.25 or G.703. So these are serial interfaces. Okay. So we use serial interfaces to interconnect WANs. Okay. So let's look at the WAN device roles. Now, when you're talking about a WAN, we have three types of devices. Really, the first set of devices are the routers that are situated at the customer's home. These particular routers are referred to as customer edge routers or device. Mm. So they are located at the customer premise and connected to one or more PEs. Now, when you're talking about the PE, this entire network here is the network for the ISP. Now, within the ISP, we have two types of routers or devices. The first set of routers are called PEs, these ones here. PEs are the ones that connect to the customer edge routers. But within that network again, we have routers that do not connect to the customer. They're just used for fast data forwarding within the ISP's network. Now, these particular routers are called the provider's device. Provider device. They're not connected to any CE. They're not connected to any CE. So those are the three types of devices: customer edge, provider edge, and provider device or router. Okay. Now we look at the early application of WAN technologies. The early WAN technologies perform different layer 2 encapsulation at the data link layer for different types of physical links. So the physical links, depending on the physical link, this is important, you can either use PPP, HDLC, or FR to interconnect either CE to PE in order to implement long-distance transmission of user access packets over WAN. Now, within the ISP's network, we normally use ATM. ATM is commonly used on ISP backbone networks for high-speed forwarding. So, while you can use PPP, HDLC, and FR frame relay, you use it here. To connect the PE to the customer edge, you use one of these protocols. This one. On the other hand, within the ISP's backbone network, we use ATM. We use a synchronous transfer mode. So I hope that is clear. Okay. So now let's look at one of the protocols that is used to connect the customer edge to the provider edge. This particular protocol is called the point-to-point protocol. So let's have a look at it. So PPP is a common WAN data link layer protocol. It is used for point-to-point data encapsulation and transmission on full duplex links. Now, PPP provides two types of authentication. The first one is called PAP, or Password Authentication Protocol, and the other one is called CHAP, or Challenge Handshake Authentication Protocol. So we're going to look at how it works. Now, PPP features high extensibility. For example, it can be extended to work over Ethernet in a protocol called point-to-point protocol over Ethernet, which you're also going to see how it works. So that's why we are saying it's highly extensible, because it can be extended to work not just with serial cables but also with Ethernet cables. So PPP packets need to be transmitted over an Ethernet. Now, PPP provides a protocol called Link Control Protocol, LCP, which is used to negotiate the link layer parameters, such as the maximum receive unit and authentication mode. So we're going to see how LCP works shortly. The other protocol it provides is NCP, or Network Control Protocol. This one is used to negotiate. So LCP is used to negotiate link layer. So that means data link layer parameters, while NCP is used to negotiate layer 3 parameters, the network layer parameters. It uses a protocol called IPCP, IP control protocol, for negotiation of network layer parameters and better support for network layer protocols. So NCP is simply used to acquire an IP address, as we are going to see. So really, you can see from this particular diagram that with point to point, with PPP, we are having like two routers. For example, R1 is the CE customer edge router, and this is the provider edge router here. And we are having the interconnection between serial interfaces. So it is PPP that is going to be able to negotiate and ensure that the interconnection between these two routers are successful, as we are going to see. Okay, so let's look at the steps on how this is achieved. Now, PPP link setup process. So PPP link setup involves three things. The first one is link layer negotiation, then authentication negotiation, then network layer negotiation. Now, link layer negotiation is used to negotiate link parameters and establish link layer connections. Authentication will either use CHAP or PAP in order to authenticate the peer. So we're also going to see how that happens. And normally authentication is optional. Then we have the link layer negotiation. Link layer negotiation is used to select and configure network layer protocols and negotiate network layer parameters. So for PPP to be able to work, these three steps have to occur. Step number one, link layer negotiation. Then if you've configured authentication, it's going to happen as step number 2. And step number 3, we have link layer negotiation. So after those 3 happen successfully, then these 2 devices will be connected via the PPP protocol. So we're going to see how each of the steps really work. Now, at this point, I just want to insist that this protocol is very important, and it's actually being used. It's actually being used, for example, when you're connecting to your internet service provider from your home fiber, your wireless router is actually using PPP. Is using PPP to get a public IP address that is going to connect you to the internet. So that's why you need to understand this. We know that the telecom network has actually transitioned to all IP, and therefore it uses the point-to-point protocol, and specifically PPoE, and PPoE encompasses PPP. So it's important that you understand how PPP really works. Okay, so this is the state machine for the PPP link interface. So the state machine. So PPP negotiation is performed by interfaces on both ends of the link. So we're going to see how the interface status indicates the protocol negotiation phase. Now, if you've not connected your device via PPP, then the interface status is dead. Otherwise, when you configure PPP between 2 peering devices, then the status transitions from dead to establish. Now, here we are on step number 1, which is link layer negotiation. Now, after they exchange some packets, they're gonna see whether it is a success, whether all the parameters, for example, match. If the parameters don't match, as we are going to see in a short while, then it goes back to dead. Otherwise, if the parameters match, then the session is opened and it checks, do we have authentication? Is authentication required? If authentication is required, and now here we are on step number 2. If authentication is required, then authentication is performed. Did you pass the authentication? If yes, then we go ahead to negotiate the network layer parameters, such as the IP address that I'm going to use. If it fails, then we terminate, and we go back to the dead state. Otherwise, after negotiating the network parameters, you can now be able to access the network or the internet and be able to send and receive data. After you're done accessing the internet, you can close the connection, and it will go back to the terminate state. It will go to the terminate state after you close from here, and after terminate, the connection between the peer and the remote device is terminated, and the state goes back to dead. So those are the three steps, really. Those are the three steps: link layer authentication, link layer negotiation, then authentication negotiation, then network layer negotiation. Okay. So let's now look at the LCP packet format. Just like we've done with the IP header, we've done with the Ethernet header, and many others, we also need to understand the link control protocol packet header. Now, the protocol field in a PPP packet identifies the type of PPP packet. Now, then we have the code field, which is further used to identify the different types of LCP packets. Now, we can see that we have the flag field. The flag field is used to identify the start and the end of the physical frame. The start and the end of the physical frame. That's why we have the flag field at the beginning and we have the flag field at the end. Normally, we call this a start and end delimiter. A start and end delimiter. It normally has a value of 0, 1, 1, 1, then 1, 1, 1, 0. So 8 bits, 0 at both ends. So it's just used to ensure that we don't lose data as we place it on the link. Used to notify the link that we've started receiving data, so that the link cannot be able to lose data. Then the next field is the address field. As you can see here, the address field in the PPP frame is used to represent a broadcast address, and normally it's a fixed value of all ones. So you can see FF, all ones. Then we have the control field. The control field, on the other hand, is used to indicate that the frame is an ordered frame. So when you get time, read more about that. Then you have the protocol field. The protocol field, on the other hand, is used to identify the type of protocol packets that have been encapsulated using this particular PCP. So it simply means we are able to know here, we are able to know whether this packet is an IP packet or an IPCP packet or LCP packet or PAP packet for authentication or CHAP packet. So that is what we have under the protocol. The protocol that has been encapsulated here within the information field. Okay, then within the information field, it can go up to 1500 bytes, and normally we have these subfields like the code field here. The code field is used to represent the specific. The code field is used to represent the specific packet that is being used on this particular packet. For example, is it a configure request? So if it's a configure request, then the code field here will store this value, hexadecimal value. Is it a configure ACK? Is it a configure NAC or configure reject? So we are going to see how each one of them is used shortly. Okay. So let's see the normal negotiation, the LCP negotiation process. This one has been termed normal negotiation. Normal negotiation means no problem occurs during the negotiation. So how does it how does it happen? Okay, so LCP negotiation is implemented by exchanging different LCP packets. The negotiation is initiated by sending a configure request packet. Configure request packet from either party. Now, if the peer end identifies, now this is what is important, if the peer end identifies and accepts all the parameters in the packet, the peer end returns a configure ACK. For configure acknowledgement, it returns a configure ACK packet to the local end, indicating the negotiation is successful. Now, normally, when we send on step number 1 here, when we send a configure request packet, we carry some parameters. These parameters include, for example, the MRU. The MRU is the maximum receive unit. By default, it's normally 1500 bytes. And then we can also specify the authentication type. For example, here we are specifying that we want to use PAP and not CHAP. Then we can also send the magic number, which is a parameter that is used to ensure that we don't have loops between these two particular routers. So those are some of the parameters that we send. Now, when we send those parameters, if the end device, if the peer device R2 is able to identify all those parameters, all those 3 parameters, then it's going to respond. It's going to respond with a configure acknowledgement. Configure acknowledgement. So configure acknowledgement verifies that the parameters of the peer end are valid. So all of them are valid. After doing that, R2 is also going to send a configure request. A configure request to R1 so that R1 can also be able to see its parameters. And if R1 responds with a configure acknowledgement, then the PPP link is now up. The PPP link is now up, and they can be able to exchange data. Okay, the next one here is an example where we have what we call a parameter mismatch. A parameter mismatch. So if LCP parameters do not match during LCP exchange, the receiver responds with a configure NAC. So NAC is not acknowledged packet to instruct the peer end to modify parameters and perform negotiation. So you can see here on step number 1, we send some parameters. MRU 2000, authentication type PAP, magic number A. Magic number is normally a random number. Now, on the peering end on R2, the MRU is set to 1500, while here it is set to 2000. Authentication type PAP. Okay, so what happens when we send this configure request? When we send this configure request, this person sees, oh, the MRU of this person is 2000, but the maximum I allow is 1500. So what do? I'm gonna here finds that a peer parameter is invalid and perform parameter negotiation. Therefore, I'm going to send a configure NAC. So this configure NAC will inform R1 that, hey, please change this parameter. I can't use 2000. And therefore, R1 is now going to change the MRU from 2000 to 1500. And on step number 3 here, it's going to resend a configure request packet that carries the negotiation parameters, the correct one now. So you can see this is the configure request with the configuration parameter modified. And after that, if this guy now is able to accept those values, then it's going to respond with a configure acknowledgement. Configure acknowledgement. So that is what we call parameter mismatch. Now, other than parameter mismatch, the other situation in LCP negotiation process is what we call unrecognized parameters. So here, LCP cannot, if LCP parameters cannot be identified during LCP packet exchange, the receiver responds with a configure reject packet to instruct the peer end to delete the unidentifiable parameters and renegotiate with the peer end. Okay, so here we want to send the configure request. We want to send the configure request from R1, but we've included one parameter here, XXX. But the peer end does not recognize that parameter. It does not recognize what XXX is. So after it receives this configure request and finds that the peer parameter cannot be identified, it performs parameter negotiation. That is, it sends a configure reject instructing the peer to delete this parameter. Please remove this. So when this R1 receives this particular configure reject, it's going to remove that parameter that is not identified by R1 XXX. So going to remove it, and on step number 3 here, it's going to resend a configure request packet that carries the negotiated parameters. So that is what we're having here. That is what we're having here. Configure request with a parameter deleted. And therefore, when this guy receives this configure request with the parameter deleted, it's going to verify that the parameters of the peer end are valid and responds with a configure acknowledgement. So that is the third situation, a recognized parameter. So I hope you understand it. And it's a common question in the exam. Okay, so PPP offers 2 authentication modes. The first one is called PAP. The second one is called CHAP. Okay. So PAP is password authentication protocol. After the link negotiation is successful, authentication negotiation can be performed. There are 2 authentication modes, PAP and CHAP. PAP authentication requires two-way handshake. Negotiation packets are transmitted to the link in clear text. So this is one of the main differences between PAP and CHAP. That when we are sending the username and the password, when we are using PAP, then we send it in clear text. On the other hand, CHAP encrypts these particular parameters. So let's see how that happens. Now, on the PPP scenario, one device acts as the authenticator. So the device that acts as the authenticator will authenticate the peer device. So on R2, we are going to configure a username and a password for authentication on S10/0/0. Now, after the link negotiation succeeds, then we are going to the layer link is established, and the authentication mode is determined as CHAP. So step number 1 here. Step number one here, the peer initiates authentication. So by initiating authentication, we are sending a packet called authenticate request. And when we do that, we send a username and a password in plain text. Don't forget that. In plain text. So this is the PPP frame, and on the protocol field of the PPP frame, it will have the PAP value. Now, after the authenticator receives it, it checks its database. So the username and password matching in the database succeeds. It responds with the PPP frame protocol field PAP, and the result is authenticate acknowledged, meaning that the password and the username has matched. So that is how PPP really works. Okay, so the next one is CHAP. Challenge. CHAP authentication requires what we call a three-way handshake. Three-way handshake. So negotiation packets are encrypted before being transmitted on the link. Okay, so just like in PAP, we have an authenticator and we have the peer. Now we configure username and password for use on the peer. Then after the link layer negotiation succeeds, we now go to step number 1. Step number 1 here begins from the authenticator. So the authenticator initiates a challenge carrying a random number. So you can see that here we are sending a pub frame. We are sending a pub frame with the protocol set to field set to chap. Then we send a challenge, a random number, code is equals to 1, like that. Then when the peer receives it, then the peer does what we call hashing. It uses a hash algorithm like MD5 to hash the ID, this ID that it has received here, the random number, which is the challenge, and a password, which is the password that you've configured on that particular interface, this password. So it combines all these three values and encrypts them. Then the peer calculates an MD value of the locally and replies with the MD5 value. So here again we are sending a PPP frame with the protocol field value being chap, and we are sending a response. So code 2 is response, code 1 is challenge, and this is the random number actually. Okay, so we send it. The name is HCIA, and we send the, so this is the username, and we send the MD5 results of the password, which is encrypted. Okay, so the authenticator performs local calculation and verifies that the received MD5 value is correct. So if that happens again, we send a PPP frame. The code is code 3, which means success, and we send a message, welcome, meaning that the authentication has succeeded. The authentication has succeeded. So generally that is how CHAP works. Now we also have other hash algorithms that are more advanced and more secure, other than MD5. So we've just seen MD5, but you can also use AES, which we saw earlier. We have another one called RSA. We have SHA-2, and we also have HMARC SHA-2. So these ones are more secure because their key length is longer, and therefore it's more difficult to crack these encryption algorithms compared to MD5, for example. So you can learn more about that when you get time, those encryption algorithms. Okay, so now after the authentication is done, then the last process is what we call NCP negotiation. NCP negotiation. Now, NCP negotiation can happen in one of two ways. We have what we call static IP address negotiation, and we have what we call dynamic IP address negotiation. So it can happen in one of those two ways, static or dynamic. Now, static IP address negotiation requires manual configuration of IP addresses on both ends. What does that mean? We've configured serial 10/0 with that IP address. We've configured this one with that IP address manually. So how does the NCP negotiation happen? It will send a configure request packet carrying the local IP address. So configure request. So R1 is sending configure request, and in it has carried this IP address 10.1.1.1. Then this one, R2, will verify that the peer IP address is valid. By valid, it means it does not conflict with any other IP address. It does not conflict with any other IP address, and it's a unicast IP address. So it's not multicast, it's not broadcast. So those are the kind of verification that is done by R2. Now, if that is the case, it's unicast, it does not conflict with any other IP address, then it's going to send a configure acknowledgement packet. When this one receives the configure acknowledgement packet, After it receives the configure acknowledgement packet, R2 is also going to send a configure request with its own IP address, and that if you want to reach me, please reach me by 10.1.1.2, like that. Then R1 is going to verify that this IP address does not conflict with anyone else and it's a unicast IP address, and send a configure acknowledgement. So after that is done, they can now begin sending data. They can now begin exchanging data. Okay. So the other way in which NCP negotiation can occur is what we call dynamic IP address. So this is what happens with your home router most of the time. Dynamic IP address negotiation. So really, you have your home router here, and you have Safaricom, your internet service provider here. So your home router does not have a public IP address. So what does your home router do? It sends a configure request packet to notify the peer end that it has no available IP address. How does it say that I don't have an IP address? On the configure request packet, it uses the IP address 0.0.0.0. So this one, the peer R2 will determine that the peer IP address is invalid and return an IP address for negotiation. So your ISP will send what you call a configure not acknowledge, but advise you, hey, use 10.1.1.1. And therefore, when you receive this NAC configure not acknowledge, you will resend a configure request packet that will carry the negotiated IP address. So you're simply sending another on step number 3 here, configure request, saying, hey, okay, I'm going to use 10.1.1.1. So this interface now is going to use the IP address 10.1.1.1. And we're going to see that when we configure this shortly. Then on step number 4, R2 will verify if this IP address 10.1.1 is unicast and it does not conflict with any other IP address, and send a configure acknowledgement. After sending the configure acknowledgement, then R2 will also notify R1 of its own IP address. So this interface on your ISP has been configured with the IP address 10.1.1.2. So it's going to send the configure request saying, hey, if you want to reach me, you can reach me on 10.1.1.2. Then your home router will now send a configure acknowledgement, and now you can be able to access the internet. So that is step number 6. Step number 6 here. Verifies that the peer IP address is valid and sends a configure acknowledgement. So that is how dynamic IP address negotiation really happens. Okay, so now let's look at the PPP configuration. It's quite easy. Okay, so to configure PPP authentication, the first thing you have to do is to make the interface to encapsulate packets using PPP. To do that, you go to the serial interface, and use the command link-protocol PPP. So if you do that, then this particular interface is going to encapsulate packets using the PPP protocol. Then you can configure what you call the negotiation timeout period using the command PPP timer negotiate, then the number of seconds. PPP timer negotiate, then the number of seconds. Now, what is this used to do? If the local end does not receive a reply packet from the peer end within the specified negotiation timeout period, the local end resends an LCP negotiation packet. So that is what this timer is used to do. For how long do I wait? If I don't receive a reply, I resend the request again. Okay. Then you can either use PAP or CHAP authentication. Here we are configuring PAP. To do that, on the authenticator, configure the authenticator. On the authenticator, create a user create a user with a username and a password, and then enable them to be able to access the PPP service, and go to the serial interface, use the command ppp authentication mode pub in order to use the pub authentication. After you've done that, you need to go to the peer, the authenticated. Now on the peer, you need to specify the username and password that it's going to send to the authenticator. So how do you specify the username and password? You go to the serial interface that is connected to the authenticator, then you use the command ppp pub, then local user, the username, password cipher, the password that you've configured. So ppp pub, then really you're just repeating this, whatever we have here. So that when this guy wants to be authenticated, they're going to send this username and this password to the authenticator. Okay. Then CHAP authentication, it's almost similar. So on the authenticator, you create a user, enable PPP service type. Then on the interface, you use the command ppp authentication mode CHAP. PPP authentication mode CHAP. Then after you've done that, you can configure the peer. So for the peer, you go to the interface, the serial interface, use the command ppp chap user, then you specify the username, and ppp chap password cipher, you specify the password. So that's how you configure CHAP. Okay, so let's look at configuration example. So here we want to enable PPP authentication on the PPP link between R1 and R2. Then we configure R1 as the authenticator. So this guy is the authenticator, and we configure this one as the peer. So remember, we are configuring PUP. Okay, so to do that, on R1, we need to create the local user and enable the PPP service. After that, we need to go to the serial interface and enable PPP encapsulation using the command link protocol PPP. Then after that, we specify the PPP authentication mode as PUP. So PPP authentication mode PUP, like that. Then you can configure an IP address on that interface. This IP address 10.1.1.30/30. Okay. Then you can configure R2. On R2, it's easy. We simply go into the interface serial 001, this one here. Then we use the command link protocol PPP. Then we specify the user and the password. So PPP PUP local user Huawei, the one we created here, Huawei. Password cipher Huawei 123. So Huawei 123. After we've done that, we can also configure an IP address. So here we are doing static negotiation. Okay, we can also see how to do CHAP authentication. So again, this is the authenticator R1, this is the peer. So to use CHAP, again you create a user and enable PPP. Then you go to the interface, link protocol PPP authentication mode CHAP. Then on R2, we go to the interface, use the command link protocol PPP to enable PPP encapsulation. Then use the command PPP CHAP user, then the username, this username that we created here, and PPP CHAP password cipher, the password Huawei 123. Okay. Okay, so let's now look at PPOE implementation and configuration. Okay, so now we look at what is PPOE. So PPOE is PPP over Ethernet So this is a link layer protocol that encapsulates PPP frames into Ethernet frames. So that simply means that we do this. Inside an Ethernet frame, we put a PPOE packet inside an Ethernet frame. So you can see that these are indeed Ethernet fields, destination mark, source mark, ETH type, and frame check sequence. And therefore, we now encapsulate on the data part of this particular frame, we encapsulate the PPP frame. Now, the reason as to why we do this is so that we can allow multiple hosts on an Ethernet to connect to a remote server. That remote server is called the broadband remote access server. Now, generally, the architecture of your ISP, for example, the ISP that is giving you fiber to the home. So you have several homes here. You have a home here. So this is a home. You have another home here. And you have another home here. So what happens is that all of you are normally connected to what we call a DSLAM. So this is called a DSLAM. So the DSLAM is simply used to aggregate all your traffic into a single fiber or channel, if you can allow me to say so. So you're all connected to the DSLAM. Then the DSLAM, on the other hand, will aggregate this traffic to a single channel, which again is fiber, to now what we call the provider edge device, your ISP's device. This ISP device is what we call the BRAS, or the broadband remote access server. Now the BRAS has several functionalities. One of them is AAA. It performs AAA, so authentication, authorization, and accounting. It's the one that is going to determine whether you are allowed to access this particular network resource. Now, normally, the BRAS sits at the edge of the ISP's network. So within the ISP's network, of course, we have other routers that are going now to route your packets to the internet. Now, really, where PPOE is implemented is between your device and the BRAS. So here we use PPOE. Because this is because Ethernet really is the most cost-effective technology among all access technologies that is used to connect multiple hosts to an access device, and that's when then PPOE is needed so that it can encapsulate these packets over Ethernet. Now, as I've said, those are the functionalities of the BRAS, and other than AAA, the BRAS is actually the one that is going to give you an IP address that you'll use to connect to the internet. And of course, that is done through PPP, as we are going to see shortly. Okay, so PPOE application scenario. Okay, so we still have it here. So PPOE provides point-to-point connections on an Ethernet. Ethernet means we are either using Ethernet cable or even fiber. So a PPOE client and a PPOE server. So your home router, you can assume that this is your home router, acts as the PPOE. Your home wireless router acts as the PPOE client. So that's the PPOE client. While the BRAS server acts as the PPOE server. So they establish a PPP session to encapsulate PPP data packets and provide access services for the host on the Ethernet, implementing user control and accounting. As I said, the BRAS server will actually perform the AAA. So PPOE is actually widely used on enterprise and carrier networks. It's a very common technology. PPOE is usually used by home users, uh, and enterprise users to dial up access to the internet. So I think I have already explained this particular architecture. Now let's see how PPOE session is established. Now normally PPOE session is established through three stages. The very first step is called PPOE discovery. In PPOE discovery, we negotiate and set up a PPOE virtual link. After that, we create a PPOE session. PPOE session is simply the PPP negotiation. So PPP negotiation, as we understand, includes LCP negotiation and optional authentication and NCP negotiation. Then lastly, for PPOE, we have the termination. So discovery, session, and termination. Termination is when the user goes offline and the client or the server then terminates the connection. So that is what we call PPOE termination. So those are the three stages of PPOE. PPOE operates using the following packets in order to establish and maintain its session. So the PPOE packet structure and the common types are as follows. Really, on the PPOE header, we have the following fields. The first one is the version, which indicates the PPOE version. Then you have the type that indicates the type of PPOE packet that you are dealing with. Then the code that specifies really the type of packet. For the type here is the type of PPOE. Then for the code is the type of packet, the exact type of packet. So the code can have one of these values here. And it can mean that it's either a PADI packet, which you call PPOE Active Discovery Initiation Packet, or PADO, or PADR, or PADS, or PADS. That's how I prefer calling them. If you have any other way of calling them, feel free to do so. So PADO, PPOE Active Discovery of a Packet, PADR, PPOE Discovery Request Packet, PADS, Session Confirmation Packet, PADS, Termination. PPOE Active Discovery Terminate Packet. Okay, the other fields on the PPOE header include the session ID. The session ID is actually important because it indicates the PPOE session. And for PPOE to be deemed established, then the client must receive the session ID from the PPOE server. And of course, lastly here we have the length, which specifies the length of the PPOE packet. Okay, so let's see the discovery stage, which is the very first stage of PPOE. So the very first on step number one, really, on step number one here, on step number one, the PPOE client will send a PADI, a PPOE Active Discovery Initiation packet. Normally, this packet is a broadcast packet. Why? Because on your ISP side, it might have more than one PPOE servers, more than one brass, for example. So all of them are going to receive it. Then on step number two, those ones that are available are going to reply with a PADO, PPOE Active Discovery Offer packet. Now, multiple servers may be available to provide client services. In this particular example, you can see that this server is not available, and therefore it does not respond with a PADO. Now, on step number three here, the PPOE client is going to preferentially select the first received service respond and send a service request using which packet? PPOE Active Discovery Request packet. So it's going to send a unicast PADR packet to one server that actually whose packet it received first, whose offer it received first. Then on the last step, which is step number 4, the PPOE server is going to respond to the PPOE client with a packet, a PPOE active discovery session confirmation packet, and with that it's going to deliver to it a session ID. So the server assigns a session ID to the client in order to establish the session. So that is how the discovery stage of PPOE works. On the session stage, this simply includes the PPP that we looked in the previous section. So it includes LCP negotiation, then authentication, then NCP negotiation. So nothing really different. So that is going to happen between the PPOE client and the particular PPOE server that offered a session ID to it. So the entire session stage, the session ID allocated by the PPOE server remains unchanged during this time. Okay, and then the last stage is PPOE termination stage. So this happens when the client wants to terminate the session. It sends a PPOE active discovery terminate packet to the PPOE server. So when that happens, the pad packet carries the session ID to identify the session that needs to be terminated. So this particular packet will carry the session ID of the session that needs to be terminated. Then this guy will reply with an acknowledgement. Similarly, the PPOE server can also terminate. Please remember this, that the PPOE server can also terminate the session by simply sending the PPOE active discovery terminate packet to the PPOE client. So the basic configuration of PPOE, normally with PPOE, we begin by creating what we call a dialer interface, a dialer rule rather, a dialer rule. So to do that, we configure a dialer rule and set conditions for initiating a PPOE session under the rule. So we can use the command dialer rule. This takes us to the dialer rule view. So you can see you can enter the ID. So here we are on dialer 1. Then you can be able to configure the username on the dialer interface using the command dialer user, then the username. Then after that, use the command. You add the interface to the dialer group by using the command dialer group, then the group that you want to add it to. Then you can bundle. You can specify a dialer bundle for the interface by using dialer bundle, then the number of that particular dialer bundle that you want to use. After that, you bind a physical interface to the dialer bundle using the command PPOE. You have to go to the particular interface, then use the command PPOE -client dialer -bundle dialer number, then the number of that particular bundle that you created. So this is an example of how to configure a PPOE client. In this particular example, R1 acts as the PPOE client while R2 acts as the PPOE server. So we want to configure a dialer interface on the PPOE client on R1, then configure authentication function on the dialer interface on R1. Then after that, the dialer interface on R1 can obtain an IP address allocated by the PPOE server. So we're also going to configure that. Then R1 can access the server through the dialer interface. So we're also going to configure that. So how to do that? You start by creating the dialer rule, as you see here, dialer rule. Then dialer rule 1 IP permit in order to be able to permit this particular dialer rule to work. Then we create a dialer interface. So interface dialer, then we give it 1. So interface dialer 1, then dialer user. We create now a dialer user on that particular interface, dialer 1. Then we call it, for example, enterprise. Then we create a dialer group and a dialer bundle. After that, we can now create or specify the username for the user that is going to use this dialer interface. So away, and password Huawei123. Then for the IP address, we use the command for this dialer interface. We use the command IP address ppp-negotiate. So that way, it's going to ask using PPP to be given an IP address by the server. Okay, after we've configured the interface, we can now bind the dialer interface to the outbound interface. So the outbound interface is GE001. So to do that, we go into G001, then use the command PPOE client, then dial bundle number 1, the one that we just created. Then after that, we configure a default route from the PPOE client to the server. So how to do that? We simply use the command IP route static, then we use the anycast address 0.0.0 and the mask 0. Then we specify that if you have any packet, send it to this dialer interface. Send it to interface dialer 1. So that's what we're doing there. Okay, so if you do that, then R1 will be able to access the server. Now, the second example here is how to configure the server. So we want to create an address pool on the PPOE server for address allocation to the client. Then after that, the PPOE server should be able to authenticate the PPOE client and assign a valid IP address to the client. So let's see how then do we configure the the PPOE server R2 here. So first we create an address pool and a virtual template. So we create a pool just the same way we've been doing it, IP pool, then we give it a name, for example, pool 1. Then we specify the network and the gateway list, the network address and the gateway list. After that, we can create now what we call a virtual template using the command interface, then virtual template, and then the name, for example, 1. After that, in the virtual template, we can specify that we want to use CHAP as the authentication mode, and we can give it an IP address. Then we can tell it for remote addresses, use IP addresses from pool, this pool that we created, pool 1. So after you've done that, you can now bind the physical virtual template, the virtual template to the physical interface. This one here, the physical interface, G000. So you get into the interface and use the command PPOE server bind virtual template 1. And then after you do that, you can now create the user using the AAA commands, local user, Huawei1 password cipher, Huawei123, and local user Huawei service type PPP. You enable the PPP service type for this particular user. Okay, so that's how you configure the PPOE server. To verify your configuration, for example, on R1, which is the client, you can verify the dialer interface status by using the command display interface dialer 1. So you should be able to see, for example, the current state. Remember, the display commands are very important for troubleshooting. So you can see that they are up. If they are not up, then you know that there's a problem. When LCP is opened and IPCP is opened, it means that the session is up and this client, PPOE client and PPOE server can be able to communicate. You can also check the initial status of the PPOE. You can check the initial status of the PPOE. The status can be one of 4 states. So to check that, you use the command display PPOE client session summary. Now you'll see things like the session ID. So this is the session ID. You'll see the bundle number. You'll see the dialer number. You'll see the interface that this particular session has been applied on, and the MAC address of the client and the MAC address of the MAC, then the state. So the state can be one of 3 states. For example, idle. Idle here means that the session is idle. and it has not actually been formed. Then up means that the session is has been set up successfully, and now you can be able to exchange data. Otherwise, the other two states include the PADI. Under state, you can also have PADI. So this means that the current session is in the discovery stage, and it means that the PADI packet has just been sent out. So we are still under the discovery stage, and we've sent out the initiation packet. Otherwise, the state can also be that, meaning that the current session is still in the discovery stage, and we've just sent out the request packet. So other than idle and up, we can have PADI and PAD on the state there. Okay. So now we look at the development of WAN technologies. I'm not going to spend a lot of time here. I'm just going to give a summary. Evolution of WAN network technologies. Now, the data link layer protocols commonly used on WANs include PPP, HDLC, and ATM. With the network evolution towards all IP, this one is important, that networks, including telecommunication networks, they're evolving to adapt an all IP architecture. So the IP-based internet becomes popular. However, IP technology is based on the longest match principles. Longest match rule, which uses software to search for routes, resulting in what is the problem of using the longest match? Low forwarding performance, which has become the bottleneck that restricts the network development. So, in order to solve that problem, a protocol called multi-protocol label switching, MPLS, was actually proposed in order to improve the speeds, the forwarding speeds of routers. Compared with traditional IP routing mode, MPLS forwards packets, passes packets, forwards IP packets, headers only at the network edges during data forwarding. Otherwise, the transit nodes forward packets based on labels. Transit nodes forward packets on labels. So instead of opening up the IP header, we forward packets based on labels, as you're going to see shortly. So without the need to open up the IP packet header. So this speeds up the forwarding capabilities of routers. Now, however, even though MPLS was initially created to solve that problem is no longer a problem because of the improvement of router performance, meaning the processing power of routers and the technological improvements of computing power and processors has actually made it possible to forward as fast as possible, even when we are using the longest match rule. So, with the improvement of router performance, the route search speed is no longer a bottleneck for network development. Thus, MPLS loses its advantage in the fast forwarding speed. However, leveraging support for multi-layer labels, so there's what we call multi-layer labels, and a connection-oriented forwarding plane. So IP is connectionless when you're forwarding using IP, but when you're forwarding using labels, then it's connection-oriented. Now, MPLS is widely applied in various scenarios, such as virtual private networks. When we want to create VPNs, we use MPLS. It's also used for traffic engineering and quality of service scenarios. So that's why MPLS is still in use up to date. Okay, so this is just trying to give you the traditional IP routing and forwarding. So I won't be here for long. Just to reiterate that the routers will forward depending on the longest match principle. The router receives the packet, looks at the destination address, searches its own routing table. Do I have this particular network? And uses the longest match principle. Then sends it, looks at the next hop, then sends it to the next hop. So sends it to the next hop. The next hop will repeat the same thing. Open up the IP header, find if search its own routing table. Do I have this particular network? And then use the longest match principle and then forward to the next hop, like that, until this particular packet reaches the destination. So characteristics of traditional IP routing forwarding: all routers need to know the network-wide routes, meaning all the routers must have all the other networks on their routing table in order to send from source to destination. Now, traditional IP forwarding is connectionless oriented and cannot provide end-to-end quality of service guarantee. What that means, connection oriented, it means that, as you're going to see, for example, with MPLS and another technology we called segment routing, you cannot be able to specify the path that a packet will take from the source to the destination. You cannot be able to specify that because every router will independently calculate how to forward the packet to the next hop, depending on, for example, the longest match, the protocol, and therefore the principle, and also a preference rather, and also the cost. So every router calculates, does its own calculation of how to forward the packet to the next hop towards the destination. So that's why you call it connectionless. But for example, in MPLS, we can be able to specify from the beginning how to forward the packet from source to destination. Follow this path or follow this other path. And that's what we call traffic engineering, or we can also say it provides quality of service guarantee, end-to-end quality of service guarantee. On the other hand, problem with opening up the IP header, searching routing table using longest match is that it makes routers to have a low forwarding performance because it takes a lot of time encapsulating, decapsulating, and forwarding it. Okay, so MPLS is a label-based forwarding. This is just a summary of MPLS. Unfortunately, in Datacom, HCAI.com, they removed the topic on MPLS, but on routing and switching it was there. So you can go to my YouTube channel, and I urge you to do so. Go to my HCIA R&S series and watch the entire topic on MPLS if you want to know how it operates. The other one is segment routing. Again, segment routing was eliminated. So here we're just giving a summary. Now, generally, MPLS is used on IP backbone networks. MPLS is what we call a tunneling technology. That provides connection-oriented switching for network layer based on IP routing and control protocols. So it provides better quality of service guarantee. MPLS labels, instead of IP routes, are searched for to forward packets, which greatly improves the forwarding efficiency. So labels used in MPLS forwarding can be manually configured or dynamically allocated using a protocol called LDP, Label Distribution Protocol. So if you want to understand all this and how it works, please watch my MPLS topic video. But generally, on the provider's network, as you can see here, this is the provider's network. We have the provider edge device, and of course we have the transit nodes or the provider node, the ones that are not connecting to the customer. So this one is the customer edge router, this is the provider edge router, and these are the provider router. So within the ISP's network, we use MPLS. When we use MPLS, we call that particular area an MPLS domain. We use MPLS to forward data. So this, let me just do that. So when this packet comes in, when it gets to the provider edge, the provider edge is going to add an MPLS label to it, so that within this network, we are no longer going to forward this packet using the IP address. We're not going to use the IP header to forward this packet, but rather we are going to use the MPLS label. So MPLS label, then we send it to the next router. The next router will know that, hey, if this packet has come with a label of, for example, 1030, then I'm supposed to change the label to 1040 and send it to this next hop. So this one is simply going to most likely change the label value, for example, to 1040, then send it to this next hop. Now, when it's getting out of the ISP domain or MPLS domain, the other provider edge router is going to remove the MPLS header and forward this particular packet now using the IP header. So on this particular device here, we are going to remove the MPLS header because we are sending it out of the MPLS domain and send it using the IP, and send it using the IP header. And then when this one receives it, of course, it's going to forward it to the destination using the IP header. So that's how MPLS works within the ISP's network. We don't want to forward using IP address, we want to forward using labels, which improves the forwarding efficiency. Okay. So when you get time, please watch that video. Now, some problems with MPLS. Now, static label distribution requires manual configuration. So as we said, the labels that are added to those particular packets can either be configured manually. So that is what we call static label distribution. So when we do that, as the network scale expands and network topologies are prone to change, static label configuration cannot meet the requirements of large-scale networks. So it becomes cumbersome to maintain. Otherwise, when we use the label distribution protocols, then we call that dynamic label allocation. When you do that, some dynamic label distribution do not have the path computation capability. Path computation capability is calculating the path cost. So most of them use IGPs like OSPF to compute the path cost because they cannot be able to calculate the cost of the path. So that's one of the problem with LDP. In addition, the control planes of this protocol are complex. That is, how to share these labels. The LDP uses so many packets in order to achieve the label distribution. So it requires devices to send large number of messages to the peer and path status. So this wastes link bandwidth and also consumes a lot of device resources, including the processing power and storage. So that's the main problem with MPLS when we are either using static label distribution or dynamic using label distribution protocol, LDP. Okay. So because of those problems, a solution was invented. That solution is called SR, segment routing. So segment routing has the following advantages. Number one, it extends the existing protocols. So it extends some IGPs like OSPF and BGP and enable them to be able to do label distribution. So it extends. So instead of coming with its own LDP packets, it uses the IGPs to do label distribution. So eliminating the need for LDP protocols on the networks, thereby simplifying the protocols. Number two, it introduces what we call source routing mechanisms. So in source routing mechanism, we are able to centrally calculate route paths. That means that on the provider edge device, on the PE, we are able to determine how this particular packet will flow throughout our ISP network. And then lastly, it allows networks to be defined by services. By services. Uh, so networks are driven by services after service requirements such as latency, bandwidth, and packet loss requirements are raised by applicants. A controller. So that is when you talk about controller, it means we have a central device that is doing all the control plane calculations, and that is what we call software-defined networks. So a controller can collect information such as the network topology, bandwidth usage, latency, and calculate explicit paths that meet the particular service requirements. So those are some of the advantages of segment routing. Again, I repeat, I have an entire topic on segment routing, which you can learn from. Otherwise, here just a summary has been given. So SR divides network paths into segments and assigns segment IDs to these segments. So segment IDs are allocated to forwarding nodes or adjacency links. So when you talk of forwarding nodes, we are simply talking of the router, for example. When you're talking of the links, we are talking of the link, for example, this link between R2 and R3. So in this example, SIDs of the forwarding nodes are expressed as 1600X. So 1602, 1603, 1605, where X is the node ID. SIDs of adjacency links are expressed 160XX. So for example, 160.2.3, 160 here, 35. Okay. So SIDs of adjacency links and network nodes are arranged in order to form what we call a segment list. Now the segment list is what we are seeing here, the segment list. So the segment list is added by the provider edge router before it gets into the MPLS domain. Or you can call it SR domain if you want to. So the segment list determines the forwarding path. So it is encoded by the source node. The source node is what you're calling the provider edge, R1 in this example, in the header of the data packet, and is transmitted with the data packet. So the essence of SR is instructions which guide where and how the packets go. So for example, R1, after adding this, it's gonna look at its database, a segment routing database. I'm supposed to send this packet to this node 16003, and therefore it's gonna send it to 16003. For example, it's R2, and then not really. After because it's connected just to R2, let me just say that again. So R1 will include this segment list on this packet and send it to R2. Now R2 will receive it. R2 will see that on the top of the segment list we have 16003, and therefore in its database it will know that it's supposed to send it to this next hop because this node has the SID 1603, and therefore before sending it to this next hop, before sending it here, it's going to remove this particular node. It's going to remove that particular entry and send it to this guy. Then this guy will receive it. Once it receives it, it's going to look at this, because now this is what we have at the top, this 16035, and it will know, oh, then I'm supposed to send it out through this link, and therefore it's going to send it out through this link, like that. Before sending out through that link, it's going to remove it. It's going to remove this. Then R5 is going to find this. It's going to look at this. Only that will be there by the time it's getting to R5. And then R5 will know that if I want to send this, I'm going to check on my table and see who next I'm going to send to. Therefore, it's going to send to R6 like that and remove that particular header. So by the time R6 is receiving it, it does not have the segment list. So R6 now is going to forward using the IP address header and send it out of the SR domain using IP. So really that is how SR works. Please watch my video on that. Now SR can be deployed in one of two ways. It can either be deployed without a controller or with a controller. When you're using a controller, then you're having a central device that is able, you have a central device that is able to read the entire network topology and compute paths. So controller is used. If the controller is used, the controller collects information, reserves paths resources, and computes paths, and delivers the results to the source node. So when you use the controller, then it has an overall view of the entire network, and it's able to act in real time because it can know that, for example, we have congestion here, we have traffic jam, and therefore it can be able now to say that for incoming packets, use this path, forward it there, then maybe this one can forward it here. So that's the main advantage of using the controller, because it has an entire view of the network, that central device. Otherwise, when you're not using a controller, then you'll have to configure, as the network administrator, you'll have to configure the segment list by, of course, using the CLI. But when you use the controller, for example, for Huawei, it's called iMaster NCE. Then you use protocols such as netconf. It uses protocols such as netconf, which is what we call netconfig, and PCP, in order to learn about the network status and be able to dynamically create different paths. So SR can easily be used to specify packet paths. So on a live network, different paths can be defined for different services when you're using SR. So in this example, 3 explicit paths are defined to implement service-driven network. One each for data download, video, and voice services. So devices are managed by the controller, which can quickly provision paths in real time. So that's what I just said. So generally, you have the controller, iMaster NCE. Now, the iMaster NCE, depending on the service requirement. For example, for downloads, it needs high bandwidth. For example, for video, it needs low latency, so the video cannot hang. For voice, it requires less packet loss. So the iMaster controller is able to know the requirement of each of these services and be able to create different paths that will meet these requirements. So the paths are created and delivered to the PE device, so that the segment list can be able to identify the paths. So for example, as you can see here, for example, for data download, or for example for voice, we can see that it's passing through this. It's passing through this channel. You can see that it's passing through here. Then, for example, for video, we want a low latency path. Then that is being done through this path. So that is the cool thing about using the controller and about using SR. This is part of what we call traffic policing and traffic engineering. And you can see, for example, for high bandwidth, we want to forward via this path for services that require higher bandwidth. So, ladies and gentlemen, that is the end of this chapter. I know it has been quite long. Please go through these questions and revise them. I hope you've understood how PPP and PPOE works, and you've also appreciated briefly the importance of MPLS and SR. Again, I repeat, find time and watch my videos on MPLS and SR because they are very important technologies for network engineers to master at this point in time. Asanteni sana. God bless you.